Hello, and welcome to another thrilling episode of Conquering the JavaScript Interview. This is the place where we arrange the stepping stones to your success. Today, we're about to climb to the peak of understanding as we dive into peak finding algorithms. So tighten your seatbelts because we're about to get coding. Let's go. So yeah, today's algorithm is a kind of algorithm called peak finding. This one in particular is going to be a very simple dumbed down version, meant for beginners to help y'all get your stepping stones arranged for success, like I said in the interview series. This one is straightforward. Write a function that takes an array of integers. Simple enough. Find a peak element, i.e. an element that is greater than its neighbors or has two smaller neighbors if you want to think of it in the opposite direction, right? So it's pretty simple. If we imagine this as a line of people with each person being the integer signifying their height, for example, we would simply have to look across the line of people until we found a tall individual with two shorter ones on their left and right hand sides, and voila, we have found a peak person in this line. That's the analogy in this case, right? Line of people, scan your eyes across until you find a peak. Until you find someone tall with shorter people on their left and right hand sides, boom, you found a peak, and the algorithm is technically solved and done in a very simple scenario. For some edge cases we can take into consideration, if the line of people is empty, we can return null because there is no peak element in a line of empty people. If it's an array length of 1, for example, that's the only person in line, that's our peak person, because technically that is also true. They don't have any neighbors that are bigger than them. So we can just say, well, it's the first guy in line. He's a peak. Or gal. It doesn't matter, right? We can also take into consideration looking at the end of the line really quick to say, oh yeah, there's a tall person at the end of the line. The person to their left-hand side at the end of the line is shorter. Like in this example here, we can quickly see that the person at the end of the line is very tall. The person to their left-hand side is a little bit shorter. Boom, we have a peak by simply looking at the end of the array and not at the beginning of the array or line of people in my analogy. But other than that, we would just scan our eyes across the way and do a comparison for each element to see if its neighbors are smaller than it. For 7 in this case, we have a 3 and a 1. Boom! Those are both less than 7, and this function could then return 7 as a peak element. However, if we scan the line even further, we can see 6 is also a peak element, as we have a 2 and a 0 that's less than it, and the 3 is as well, as 0 and 2 are less than it. So we can also talk about an alternate implementation that returns all peaks and not just the first one. But to keep it simple, let's just return the first element to see if we can get this figured out. So clearly we're going to have to do some iterating and a couple of edge case scenarios to account for in our function, and then we're going to go ahead and convert it to write to look for all peaks. But like our inputs here, see this one 1, 2, 3, 4, 5. The only one is at the end of the array, and then 5, 4, 3, 2, 1. That one's instantly at the beginning of the array, so those should be quickly solvable with our edge cases that we're going to be writing here in just a moment. Right, so getting underway, we can say if there is no array length whatsoever, that's when we can do an early return of null, as that can tell our that output should tell our testing or whatever we're doing here that, well, there are no peak elements because there is no array length, there's no input. So boom, quick little edge case we can throw out right there. Like I had mentioned in our little mini analogy with a line of people, if I start at the first and last people and notice that they are whatever height, and if the person to the right of the first is short, boom, we're good to go. Or if the line is 2 people, we can find a peak very quickly as well. So we can say, or 1 person rather, if the array length is 1, or if it's a line of 2 people, and that's the case, then we can quickly return our array 0. This is simply checking, and we should probably write the keyword return, shouldn't we, folks? That's checking to make sure that if there's a line of 2 people, that the person on the left-hand side, the first index, aka the 0 index, is the peak individual in our line and immediately returning them if that's the case. Then we can look at the end of the line to see if that's if the person at the end is a peak or not. We can do that by saying the length of the array minus 1 will always be our final index position. It's something I've been drilling in y'all's heads in this series fairly regularly. If they are bigger than the person to their left-hand side, which is going to be the end of the array minus 2 spots, like that. If that happens to be a true case, then we can return the person at the end of our line like so, because boom, we've quickly found a peak in this particular case here, right? So check for one element or two elements to quickly determine a peak. Check last element, right? Check for any elements at all. Those are our little edge cases, our corner cases right here. We're going to take into consideration to quickly pump out some answers from this little algorithm, right? Okay, now that we got those out of the way, if none of those have returned a peak very quickly, then we're going to have to actually iterate through our array, right? So we're going to say a for loop. Now, because I've already accounted for the fact of looking for the first element being a peak, we do not have to start our loop here at an index of 0. So I'm going to choose my iterator to be assigned a value of 1 rather than 0. We're still going to go through the rest of the array length, incrementing by one index at a time. And here's going to be our if case to return a particular peak element if we happen to find one. But we have to say, is the individual we're looking at on their left-hand side shorter? And is the individual on their right-hand side also shorter? So we're going to do that by saying, hey, if the element or the person we're looking at is taller than the individual on their left, right, there we go. And if the individual we're looking at is taller than the individual or element on their right, that means we found a peak, and we can just quickly return that particular element that we're looking at, right? And if that loop happens to finish and none of my edge cases up here have caught any kind of peak whatsoever, then we're also going to return null to indicate to our tests, if we have any, that test this particular scenario, that there are no peak elements in this array. Maybe it's an array of a bunch of the same numbers or something like that. So, yeah. We should be good to go to actually test this. So, yeah, like I said, if there's no length, just return nothing, or null rather. It's different than nothing. If it's just an array length of 1, go ahead and return the first element. Technically, that's a peak. Otherwise, if it's an array of 2 elements, we're going to check to see if the first one is the tallest, so we can early return them. Then we're going to look at the end of the array to see if that's a potential peak. Otherwise, we iterate starting from index 1 back to the end of the array to try and find a peak somewhere in the middle here. Otherwise, if all else fails, then somehow we have no peak and we were going to return null from this function anyhow. So let's run a couple console logs from my inputs up yonder to see if it works or not. Let's copy this first one, find peak with that array. Once again, 1 is less than 3, and it has an array input, so the first return null is not going to catch. It's an array length of not 1, so that part doesn't work, but we have an OR operator saying OR is 1, the 0th index, bigger than the first index. It is not, so it doesn't do that. Then it goes to the end of the array and checks to see if 2 is a peak. 3 is definitely bigger than 2, so that doesn't pass the test, so it starts at 1 and then iterates. It will look at the 3 and say, is it bigger than 1? It is. Is it bigger than 7? It is not. I iterates plus 1 to the second index position. 7 is greater than 3. It's greater than 1. Boom. That should output our peak. And it does. That's what I'm talking about. Then we have the other two find peaks that are straightforward. An array of 1, 2, 3, 4, 5. The combination of my luggage. There we go. Oh yeah, I forgot to console clear between these so we don't get the repeated spam. There we go. Yeah, so we get 1, 2, 3, 4, 5. It checks the beginning. Nope, checks the end. It's bigger than 4. Yep, we got a peak with a quick edge case without having to iterate through this thing at all. Then we're going to have our reverse version of this, which is 5, 4, 3, 2, 1, which hopefully my initial edge case should catch this one and also return 5 because it's going to look at the 0th position, determine it's bigger than the 4, and then the index of 1, and then boom, we have the element 5 as one of our peaks. And you could also choose to return the array index if that's what you wanted to do. Like it'll tell you, you could always remove the square bracket array part around these answers and just return the index position of that. So it's a really quick and easy pivot if you need to answer. If the question you happen to get asked in an interview is a variant of this that says find the peak element index or something like that rather than the element itself. But that should be a straightforward transition should you need to do that. But there you go. Like I said, it's going to have some quick edge cases to handle quickly finding peaks without having to iterate through anything. Worst case scenario, we iterate through every element once to try and find a peak. Which leads me to say that this is going to have a big O time complexity of big O of n, our favorite friend, the linear line, just a whoop slope, because the bigger the input gets, the worst case scenario, it means we're going to have to iterate through every element at least once. So big O of n, bigger the input, the more operations we have to do with the one iteration. It'll have a space complexity of a big O of 1, because the only variables we really have are like the iterating variable that we would have to increment over time, and that pretty much has a complexity of 1 for space, because it's not that that's not that big of it doesn't take up more and more memory, right? It's just going to be a number that grows over time. So yeah, pretty simple big O complexity for this one, big O of n for time, and then big O of 1 for space. Now, like I had said, we can have a secondary version of this where we can have the find all peaks function right here. And we can have a version called find all peaks that takes the same input array, and it should return possibly, let's think maybe like an array of all the peaks that it found in a given answer. So it should be just an array of 5 for this one, an array of 5 for this one. But like we had deduced earlier in this video, we found that it was 7, 6, and 3 as our output. So we should see an array of 7, 6, and 3 as an output array for this version of the function. So let's go ahead and give that a shot to see if we can figure it out. So rather than copy and paste all that code, let's have some more practice by writing out this individual code here. So I'll say const peaks is going to be an array, and regardless, at the end of our entire function, it's going to have to return the array one way or another. We can do an early return just like before to say if there is no array input length whatsoever, then we can just return an empty array back to us because there are no peaks. We can then check the first element of the array and say if the array length is 1 or the array index of 0 is greater than or equal to the first element of the second element of the array. That means our first element, aka index 0, is a peak, just like before. So we can say peaks.push the element. So you can see it's going to be really similar to our code from before, but instead of just returning right there, we're going to push elements into an array and then just return the array at the end, which would be the only real modification. Here, it depends on how I wrote my test. I can't remember, but the order of the numbers technically doesn't really need to matter. It doesn't have to be a test that returns 7, 6, and 3 exactly. So you could have your last element check above or below the iteration, and the answer would still technically be correct. But again, the tests, I need to make sure I wrote that the order of elements is not important, just that their value is. So I'll double check the tests before pushing this to the repo that I'll start putting in, that eventually I'm going to start putting in the description down below. So we're going to say if our array element at the end of the array is greater than or equal to our array element to its right-hand side, that means we have a peak at the end of the array. So we can say peaks.push array length -1, representing the end element of the array. After those 3 edge cases are handled, we're going to go ahead and iterate through the rest of the array, just like we did before, with our classic little for loop starting at 1, since we already checked the 0th index position. And it'll be the same condition, where we're going to say if the current element we're looking at is greater than or equal to the array element behind it, not r-1, but i-1. My bad, y'all. And if the element we're looking at is also a peak compared to the element to the right-hand side of it, represented by i+1, then we will push into our peaks array the array element we are looking at, and we should wind up with the wrong answer. Okay, let's see. How did I manage to muck this one up? Because that right there should have passed our last element test, but for some reason it didn't. Did I typo something somewhere, y'all? Peaks push. It is a typo. Interesting that it still worked It didn't throw an error, but it just had me giving me a typo right there. I love how this is still not working. Oh my goodness. Man, so many typos. There we go. Oh, Typo City. All right, yeah. I'm not editing that out because that was funny. At least I think it's funny to watch me make dumb mistakes. Keeps me humble, right? But there you go. I knew it. The code was right. I just wrote it wrong. In my head, it was correct. I promise. Anyway, there you go. There is the find all peaks version of this. Similar logic, except instead of returning that array element, we push things into an array that we then return at the end of our iterative process, or early if there is no array length whatsoever. But there y'all go. There is our lovely functions coded to work here. I think I have some tests on this, and again, I just reminded myself to double check to make sure that the array, order is not important, just the values. Because again, because of the placement of this if statement, if you place it after the loop iteration, then the last element will be before any other elements it finds. But if you move it to after the iteration, the last element check will always be the last potential element pushed into the array. So I need to make sure the tests don't care about the order of this. So that's something else to keep in mind if that's something your interviewer does ask you for, challenge you for, if you happen to answer this very quickly and they want to see if they can push you further. But two cool solutions. The big O for this one, for all peaks, we're still iterating over all elements at least once, so the time complexity is still going to be that linear big O of n. And in big O notation, this one will have a slightly different space complexity, because unlike the previous solution of find a singular peak, where the only variable really had was this iterator, which is just a big O of 1 as it increments by 1, we now have this array taking up new memory or space, and this array will grow kind of in the same fashion as the array, but we can't say it's a space of n, because theoretically there's not going to be probably a case where the amount of peaks is the same length as the array. If there's going to be peaks in this array, then theoretically it will be a shorter space than the input array itself. So in big O notation, we often refer to this as a space of m, where basically m is just a shorter version of our input n. So the space complexity is considered m because, again, it will find some number of peaks that's less than our input of n. So that's a big O complexity space of m. That's what that represents. In terms of why this one is cool, like I said, these are called peak algorithms, and you will see them all over in technology and computer science. Anything when it comes to like signal or image processing, if you can imagine identifying waveforms in a signal that's coming at your way, finding peaks in time-based waves, very, very important to know how to find peaks. Image processing, same thing. If you're doing some kind of like computer vision or image processing, finding peaks this is like the fundamental concept of how you're going to be finding objects specifically in an image, or our computer vision is going to start recognizing objects on a road to avoid them or something like that. And then, as always, like in machine learning and data analysis, being able to forecast and model stuff based on finding peak values that can help you build patterns and things like that. Very important stuff here. So this fundamental cool little algorithm can have some bigger implications in programming and computer science in general, which is, again, something I try and do for these videos. Like, I think it's important to know not just the boring stuff of how to solve this to pass your interview so you can go style a button to look different or bigger according to your client's needs. I want y'all to know that these actually have some kind of implication other than that, right? Something more fun than that. But anyway, thank you all for watching. Hope you found this video helpful in your journey, our journey to become better developers. If you enjoyed this video, give it a thumbs up and consider subscribing to our channel for more videos like this. I'd love to hear y'all's thoughts on this or alternative solutions, if you can come up with any, or better ones than this. If you have any suggestions for them, remember, positive and constructive comments are always welcome here. So let's keep this discussion going and help each other, you and me, improve our coding skills. So thanks again for tuning in, and I'll see y'all in the next video.